start like that. A is your initial value. This is initial, what you start with. B is your rate. And again, we said when it doubles, your rate is at 2. Triples, your rate is at 3. Half-life, your rate is 1/2. There's your decline. Now, sometimes in some of the problems it said like your population decreased 2% a year. You can't say times 2%, but you can use the 1 plus if it's increasing, the 1 minus if it's decreasing. There is never an end here. The only time we compound is with your interest, your money. We never compound on your bacteria or your half-lives or anything else. There's no end here. So it's just real basic to this. So we say, okay, assume your bacteria doubles every 3 hours, and that initially there are 2,500. So let's start. Initially, 2,500. We're doubling. So what's the rate? 2. Okay, we got a y equals. And our time is in hours. But instead of going every hour, what are we doing? Every 3 hours. Now remember I said yesterday, if you try to do this logically, it'll make sense. And then when you put it in your calculator, you'll see if it's the same as your table. So if you started with 2,500 units of bacteria, after 3 hours, this doubles. What should this be? 5,000. After 3 more hours, this doubles. 10,000. We should be able to see this. So right away, we can even answer the second part. When x is 6. This is when x is 6. You can do this in your y1. Pull it off your table. Or when x is 6, all you have to do is not in your y1, in your calculator, do this. 6 over 3. And that'll say 10,000. Okay? That's without your y1. Don't put the 6 in your y1 or you're going to get a straight line. You'll have no variable. Your variable here is the when part. Determine when. When is your time? You have to have a variable. So, and if it's in your exponent, right now, all we know how to do to solve it is by graphing. Next week when we do logarithms, we can use your pattern rule and pull the x down. But until then, we can't. Now, setting up your window is always tough. So let's think about it. We said your mins are always 0. Your x min, your y mins are at 0. It has to be in quadrant 1, which is, this is what it's asking for, the situational part of the graph. It said it wanted it over a 24-hour period. So what should your x go to if your time is in hours? From 0 to 24, right? So your x max should say 24. Your y min is 0. Your y is measuring how much bacteria you're accumulating. Now, this one says, when will it be 100,000? So we have to go to at least 100,000. So I'll make your y max be 110,000. You can make it 100,000. It'll just sit at the top. So when we graph this, all of your graphs look the same for your increasing. It doesn't start at the 0 because it started with some units of bacteria or we wouldn't be able to grow. So we kind of don't start at the 0. We started with the 2,500. When you're finding this part of it, again, we can't do this algebraically. You can only do it on your graph. So we're going to put this in your y2. And we're going to watch it, and we're going to intersect. We're going to do an intersect. And when you do your intersect, this x, this is your time. Your time tells you when. Okay? I don't have the answers in front of me. Does it make sense? If you struggled with it last night, are you seeing where you went wrong? Okay. to me, otherwise I don't know either.
So that straight line is 100,000, right?
That straight line is 100,000.
Where it intersects, what is that?
That's the point when your y hit 100,000. Right now, the only way you can solve this is with a graph. Because if I plug this in, algebraically, I got to pull this down. I have to do a log of both sides. We would have to divide by 2,500, then take the log of each side, use your power rule to bring down your variable. We're only solving graphically. So to do that, we put this in y2, we put this in y1, and where they intersect, you'll find your time that happened. I don't know if I have that. Let's see if I have the answers to that one. Oh yeah, I do. Okay. So your x happened to be 15.966 hours. Now, you were okay because you let your hours go to 24, because you were trying to do a graph over a 24-hour period. If you set your x to 10, what would happen is this. There's your graph, and you wouldn't see it intersect. You would see this graph, well actually it would go like this. And your graph would be like this. You wouldn't see it intersect. So you know you have to expand your x. Okay? Questions? You good with this? Let's hit a couple of these different problems. Let's hit the next one. Anybody have trouble with the population one? Okay. Again, we're going to start with your basic equation. You have a population of a town at 123,000, and it is decreasing at 2.375% each year. So each year, you're going to subtract 2.375% of their population. You want to write the population P as a function of time. That's your equation. That's this. So y is equal to, this is your time right here. It's as a function. Your variable is what your function is of. So we began with 123. Our rate says, are we doubling, tripling, halving? Nope, we have a little bit piece of a percent. And we're decreasing 1 minus your rate. And again, move your decimal. You got to include the whole thing. This is your 1 minus the rate. And x is your time. X is time. And time is in years. Lay out all your pieces. Okay? Now, what's nice is, when I graph this, they say, what kind of situation is this? I say, okay, if I was to graph this entire graph, I would be decreasing. It would come like this, somehow, right? But my situation says, oh, you can't use negatives, time, you can't use negative population, so you're only in quadrant 1. Your window is nice on this because your mins and your maxes are at, your mins and your, on both of these are at 0. Your y max is easy because you're decreasing. This is the highest it's going to be. So make it 125,000. You can leave it 123,000 because all it does is start at the top. Your x max, that's what you got to play with. How many years is this going to take me? I don't know, I'll say 20. By the time I get to 50,000, I might have to increase it a little bit more. I'm not really sure where it's going to go. If I don't see them intersect at the end, then I'll know something's wrong. But to graph it, you will see a decreasing graph. Oh, just keep it on this side of the graph. You will see it decreasing. Now, when you want to know when your population will be 50,000, that goes in here. Again, it's just like the other one. We really can't solve this yet because we haven't gone over the logs. So algebraically, we're going to hold off till next week, but we can solve it graphically. This is your y2, this is your y1. Let it intersect. Wherever it intersects, that's how long it will take. Now, you might have to expand your x values. You might not see it intersect yet. And as a matter of fact, x is 37.45 years, so make x be at least 40. So when it crosses at the 40, when x is, well, make x go to 40, it'll cross at the 37.45 when you do your second calc. Can everybody do an intersect? Second calc. Hit it 3 times. What it does is it starts the little flasher thing on both of these, and by the time you hit the third one, it does the intersect. Make sense? But we still, notice guys, we still keep the same format. It still is the same, only this time my rate has a decrease in it. It is not going down by half, it's not doubling, it's not tripling, it just has a decrease in it. But we never have a compounding in this, ever. Want to do the half-life one? Do the half-life too? Okay. Everybody okay with this? Christian, you okay with it? Okay. Half-life. Again, let's start with this. So, the half-life of a certain radioactive substance is 14 days. That means it takes 14 days before it's cut exactly in half. And days is your time. That's your time. There are 6.58 grams initially. So we want to make a graph of this over time. So we start with our basic equation. How many is our initial amount? Okay, my rate. What's my rate? Half. I'm decreasing. I have a half-life. Now, x tells me I'm decreasing every day. But how many days until I get exactly a half? 14. There's my cycle. Now, if you think about it, on the side, at the 0, you started with 6.58 grams of this radioactive substance. After 14 days, you were exactly half. So if you take half of this, you have 3.29 grams, exactly half. Another 14 days goes by, you have exactly half of this. Something like that. Well, what happens when you decrease, you will never go to 0, because there's always something you can take half of, which makes sense. Because your exponential curves, don't they use that as an asymptote but never touch the x-axis when y is 0? So we follow your exponential curve. You're decreasing. This is what my graph looks like. Okay? A complete graph of just your equation would come from here. Your situational graph is this. We can't use negative time, negative substance. Now, when will there be less than 1 gram? In the past, I used an inequality for this, but since it throws everybody off, I think a better way to do this is just take your 1 gram and put that in here. And do an intersect. This is y2, this is y1. Do an intersect. And when you intersect, you will find that x is 38.053 days. I rounded. So what you could say is, since you want it less than 1 gram, that the time in days is less than 38.053 days. If you want to say it that way. If you don't want to put the inequality in your statement, I need less. I need this to be less than this. So I need to have an inequality here. So if you don't want the inequality there, since we've been using it as an equal sign, take what you get and just say, just slightly less, a little tiny bit less. And it might have even taken it up in the slack of the rounding. I don't even have what I rounded from. time actually has to be greater than 38 days. Like 38.053. If it's 38.054, you're already less than 1 gram. Okay? So you're still working off your same basic formula. How'd the rabbits go? Okay, let's take a look at your rabbits. Okay. Assume that the number of rabbits in a certain population doubles, here we go, doubles every month, month is time, and that there are initially 20 rabbits when you start. So here's your basic equation. So we start with your 20 rabbits. What's our rate? 2, we're doubling. X is time in months. Are we okay leaving it in X? Every month, every X. Now, we want to know, okay, we draw a graph. We know we're increasing. Our graph is going to look like this, isn't it? Don't they all look the same, basically? Any increasing, decreasing? During your first year? So if you were going to set your window, what would your X max be? Be what? You're talking months. Your time is in months. How many months in a year? 12. So if you're just going to draw a graph of this, your time is in months. Without doing the rest of it. Without doing the rest. So if I just want a graph of your first year, you're going to go from 0 to 12. Remember, a year has to be converted to months because your initial part says every month. Now, from here, it says, how many are there after 1 year? Well, if you put this in your calculator, if you look at your table, you're looking at X of 12 to find 1 year. After 5 years, what is X? 60. If you put it in your calculator, that's what you're looking for. That part you don't even need your calculator for, because all you have to do is substitute in X equals 12, X equals 60. Okay, it's a heck of a lot of rabbits. This one, you can even just leave it in scientific notation. On your calculator, it says E19. That's your scientific note. That's your exponent for your scientific notation. That means move this 19 decimal places. That's a heck of a lot of rabbits. And this answer was 81,920 rabbits, just even after 1 year. Determine when your rabbits will be 10,000. That's the 10,000 goes in here. And just graph it. Graph your 10,000. Now you may have to expand your X max. In this case, you didn't. In this case, we didn't have to. Because after 1 year, there were 81,000, so it has to be before 1 year is over, right? So you would make it on your graph. Do you see the similarities? When we're increasing, when we're decreasing, doubling, tripling. Was there another one that troubles anybody? And I'll go over the answers, but is there one you want to work out? The left. Is that a half-life one? Okay. Let's speak to that one. And then I'll bring it up and just go through the other answers real fast. Well, I'm going to have to write my stuff up here. The half-life of a certain radioactive substance is 1.5 seconds. This is your time. Does it say every second? No, every 1.5 seconds. So we know time has a cycle. Okay, let S be the amount that you initially begin with. So they didn't give us our initial. Again, we're going to start like this. This time, I don't know what my amount is. But I'm half-lifing, so what's my rate? 1/2. Okay, now, you want to take your seconds. Your seconds is your time. So you say to yourself, are you every second? No, you're every 1.5 seconds. If I was every second, I'd be X. But since I'm every 1.5 seconds, I have to make my cycle. Make sense? Okay. Now, there's your algebraic representation. It's just your equation. Draw a complete graph of this equation if there are 2 grams of the substance initially. So we're going to substitute in a 2. Sorry, I have to work up here. Okay? So again, you're decreasing. You know you're going down, decreasing, so you know it's going to look like this anyway. You almost know what it's going to look like. An increasing versus a decreasing. They all work the same. Now, draw a graph of your problem situation. Problem means your situation only can exist in quadrant 1. What is the initial? Then they changed it on you. What is the initial amount necessary if you were to be 1 gram left? So let's do this part. 1 gram left. I don't know what my S started out with. Okay. Now, you still have one extra variable. So they've got to give you one more piece of information. You have this one, you have your X. So what other piece of information did they give us? After 1 minute. But I got a problem because my time is in seconds. I can't put 1 in my X. 60. So I can put 60 in here. Okay, now remember, this exponent only goes to this one, not the X. So I can divide both sides by the same as we did in your homework problem. Both sides divided by this. And you'll find your S, what you initially started with. And it was a big number. It was a scientific notation number. E to E12. It would say on the end of it, E12. You started out with a lot. And you went 1 minute. Remember, this is half-lifing every second, every 1.5 seconds. So if you're dealing with minutes, you have to convert. They didn't really ask you much to do about when the 2 grams were in there, other than the fact that you just had to graph it. And they all graph the same. Okay? I'm just going to hit the answer key so you can see the rest of the answers. The ones we didn't do. I think we went through most of them.
We assume do 5, 6, and 7.
5, 6, and 7. 7, thank you. Right in a row. Perfect. Okay? Here's your town. And instead of decreasing, your population is increasing. So instead of the 1 minus, your rate is a 1 plus. Oh, and I apologize, for some odd reason, this information shifted over this piece over here. So see all this red? It actually belongs up there. I don't know what happened. So we'll just have to kind of read over it. So we plug this in. You began with 475,000 people. You increased at a good rate, 3.75% each year. And X represents your time in years. And again, you wanted to know when would you reach 1 million. And you'll have to do an intersect with this, a graph and an intersect. Now, your X min and your X max, Your min is a 0. Your max is years. So if you don't know how many years, I usually say 10, 20. Start with 20. You'd be a little off and go to 30. Go to 40. Whatever it is that takes you there. Your Y min, start at 0. And your Y max, 1 million is what you're going to run your line with. So maybe make it like 1,100,000. Just so that it doesn't sit at the top. It can still sit at the top of your screen and intersect. It'll still work. And do an intersect. Good? Okay. 6. Now 6 was a little tricky. It works the same way as the one we just did. We're increasing your population. But the only thing is they wanted to know the population in 1915, 1940. Now X is time in years. So you kind of have to, they gave you the original population from 1890. That was your base year. That's the beginning, the base. Instead of the 0 year, you're in 1890. So you had to first subtract, let me just move this down. You have to first subtract and find out what your X is in terms of years. Years away from 1890. So 25 years was from 1890 to 1915. 50 years was from 1890 to 1940. That's what goes in here. Was that a little bit confusing? You can't put the 1915 in there. And you don't even need to put it in your Y1. You can just put it right in your calculator. You could graph this in your Y1, of course, and look at when X is 25 in your table, and when X is 50 in your table. If you do it that way, that's fine too. Probably even easier. And your last one, number 7. It's a half-life, and it halves every 65 days. Days is your time. So X is time in days, but every 65, there's your cycle. So do you see it real similar to the ones before? We did one that was like less than 1 gram. If it disturbs you using an inequality, use an equal sign, and then just say that you have to be actually more than this many days. Well, there'll be less than 1. You have to say less than, well, actually you just have to say X has to be greater than 117.478 days for you to be less than 1 gram. If you'd rather set the other one up as an inequality, it'll work itself out that way. And you'll get your less than sign, your greater than sign in there. Good? Now, today's a little easier. Today, 5 minutes. So we only need 5 minutes for this. That's all we need for this. I'll show you how quick this is. Oops, it keeps knocking me. Okay, we're going back to your investments. So, and you actually did these before. So start like this at the top. This is your compounding formula. Remember, N is how many times a year you compound. If it's monthly, what is N? 12 quarterly, 4 yearly, 1 annually, 1, yeah, semi-annually, 2 daily, 365. If you're continuously, you are per. Okay, so here's a compound continuously. We want to know the initial value. Look for what you're looking for. Up, of we know your initial value. We know your initial value. We want to compound this in continuously. This is your PERT for a rate for 6 years. This is your time. So you have all your pieces. Just plug it in. You got to do continuously. What is it going to be if I invest $2,575 at a rate, put your E there, at a rate, convert that to a decimal for 6 years. And just throw that into your calculator. You didn't have to graph this one because you have all the pieces. You have to graph when you have a variable because we didn't do the log part yet. So if you throw this into your calculator, and remember, money has automatically 2 digits. You will have $4,161.39. Let's hit this one, number 2. Determine when an investment of, there's your investment, accumulates to a value if it earns 9% quarterly. So you're going to start with your big formula. Hang on, guys, let me just do this one. Plug all your pieces in. Your investment originally is $2,300. Your rate is 0.09. Quarterly, what is your N? 4. 4 times T. T is the when. T I don't know. And when will it be? 4150. Now, because this is your variable, that says 4T. Because that's your variable, you're going to put this in your Y1, you're going to put this in your Y2, and you're going to see where they intersect. Same as like last night's problems, but this just has a compounding thing in there.
What's the Y1?
Y1 is your original equation.
Why are we doing that?
Because you got to see where they intersect. You have a variable in your
Whatever
X function. At time, because time is your exponent. You can't do it algebraically yet.
Right.
So that's your Y1, and your Y2 is the same concept as last night. You know how you had to find the time? You have to graph it to find. Now, let me just give you a hint on one other thing. There's one, guys, give me 1/2 of a second, and I'll explain something else. There is one that says your investment doubles. Your investment doubles. And say they're compounding continuously. Let me show you something. If I invest 100, what is it going to be? 200. When you divide this, it's 2 to 1. Whatever the rest of it happens to be. So it's always 2 to 1. Whenever something triples, it's 3 to 1. Because no matter what you put in there, when you divide it out, it's 2 to 1. It doubles. So when you see your investment doubling, here's your PERT. 1 E R T. Okay?